Um, since I'm probably slightly less familiar to many of you than the other illustrious lecturers, I'm Norm Yao. I'll talk a little bit actually about experimental work in my group on high pressure superconductivity in superhydride materials. But in particular, the measurements and the way we do those measurements for these superhydrides are done using a technique that perhaps isn't quite as familiar to folks who are sort of studying superconductivity and condensed matter theory more generally. Transport type measurements, what we've heard from Professor Chubukov, scattering or diffraction measurements. So I figured that it might be helpful for me to start with a little bit of a theory lecture first, so you hear from me twice today. The first lecture will be a little bit of a theory lecture that tries to introduce a concept that you guys are all very, very familiar with, doping or changing atoms out of a material. But it'll introduce it and ask the question, when can this type of defect in a material be thought about as a useful sensor for interesting external phenomenon? So I'll try to, hopefully it's a topic that maybe even some of the lecturers can learn something from. So I hope I'll get questions from all of you. I've chosen to sit. It'll look a little bit weird. I still will look at all of you and interact and ask questions, but my handwriting is not known to be the most beautiful, and it gets worse if I stand and write. So please call out with questions, especially because the topic here is a little bit different. We'll get very deep into superconductivity in the second lecture, but for now, let me introduce a little bit of interesting physics to you. Good. So the topic, very broadly speaking, is about how to measure superconductivity. But as you'll see in the very, very beginning, it's a topic even more broad than just superconductivity. It's about how to measure, in particular, external fields. And given that we're at the National High Magnetic Field Laboratory, how, for example, to measure external magnetic fields that come from a material. And you might say, well, there's already lots of really good ways to measure external magnetic fields. We know about scanning squid magnetometers. We know about lots of ways to do this. So what's the reason why Norm is introducing another strategy? Well, I would argue that one, you'll see that this particular approach that I'll emphasize allows one to access different parameter regimes in terms of both spatial resolution and frequency compared to conventional probes. And also, especially in the second lecture, so you have to hold your belief for a little bit, it is, I would say, the only game in town for certain types of measurements are superconductors, especially those in the high pressure context. So that hopefully motivates things a little bit. Okay, so the question is, when is a defect material a sensor? And in particular, I'd like to argue that one way we can think about this in a language that's familiar to a lot of you is that there's maybe kind of a dual role of doping a material. There's one version of the term that you're all extremely familiar with, even more familiar than me. So for example, when one writes down something like Bisco 2223, what one means by that, of course, is a chemical formula that involves Bi2, Sr2, Ca, Cu2, O8 plus X, or for example, X, iron. You're all extremely familiar with thinking about materials where X acts as a dopant. In this case, for example, I guess fluorine dopes oxygen. You're used to thinking about this X being some reasonable fraction. The second, as I read, it turns out that you replace, for example, some finite fraction. And if I'm writing too small, which I have a tendency to do, please do call out and let me know. Too small? Okay, let me write a little bit. That's okay, me too. I'm sorry. Well, yes, I promise to try. I cannot say that I will not degrade back to 1, but I'll try. All right, so for example, you replace some really finite fraction of the atoms to another. changes the level of a band structure, or it could be, in the context of this audience, macroscopic changes in the properties of transport of the material, for example, from a metal to a superconductor, as we've heard of. In particular, I'd like you to think about a totally opposite limit, the opposite limit of this problem. Sorry, I'll try to leave some things up. And in particular, I'd like you to think about, it's still changing atoms out of some material, so in essence still doping, something you're familiar with thinking about, but I want you to think about a very different, I'm going to be mainly talking about, for example, individual, so one, defects in a material. And unlike now changing the global properties, for example, changing the material's band structure or its transport properties on some macroscopic scale, I'd like you to think about this individual defect in a material as some type of localized degree of freedom. I haven't yet told you what this is. Some type of localized degree of freedom. And the idea of making it or thinking about it as a sensor is super simple. It's a localized degrees of freedom whose properties will change or can change in response to some external perturbation. Right? This is totally the essence in which we're thinking about such a system as a sensor. Right? So, very similar context to things that you've thought about before, but now I'm in a very different limit where I'm thinking about a very, very localized object, one atom, for example, changing in a particular material. But it turns out this definition that I have here, this notion of a sensor, so some localized degree of freedom, once you change out some atom in a material whose properties change from external perturbations, this is everything. This is everything. As long as it's chemically allowed, I can material, and it will certainly be sensitive to stuff that happens externally. So this kind of is a very, very broad definition, maybe too broad. So in some sense, the other requisite properties that are useful, maybe at some fundamental level, sort of the zeroth property, is that you'd like this degree of freedom to actually be pretty well isolated from its host itself. So if you imagine the defect living in the host material, you'd actually that this localized defect is actually pretty well isolated from the host itself, so that it's not just sensing stuff that happens in the host, but it is able to actually behave as a sensor of external perturbations. Done, some signal that you have accumulated. So seems very, very basic and almost tautological at some level that if you wanted to have a defect, this is what you like to do. So the topic of today's first lecture is going to be all of the defects that are in related categories. I should say that even though there is this very general sentiment that I'm giving, which is about the general properties of defects in materials and when they became sensors, it turns out relative to the full gamut of different host materials that you can have and different defects that you can have in those host materials, the number of those defects that are actually useful sensors is essentially a vanishingly small fraction of those. It's like a measure zero set of those. So it's really very, very special systems that you can think about and ultimately behave as useful sensors. And the topic today is something that I think some of you will have a little bit of familiarity is something called the nitrogen vacancy defect, or the nitrogen vacancy center. Nitrogen vacancy center or defect inside diamond. Okay. So, as we've stated here already from the outset, it turns out the host material for this defect, is diamond. And diamond, of course, you have a semiconductor, but a pretty wide band gap one, with a valence band and a conduction band that are separated from one another by about 5.5 eV. And in particular, diamond in its optimal native form is very simple. It is the strongest material, and it has a structure that is a tetrahedral arrangement of carbons. 4 valence, likes those 4 bonds, and it does so with sp3 hybridized orbitals like this. So, in particular, the NV center corresponds to a situation that happens inside the diamond lattice naturally, where 2 of the very most common defects inside a diamond lattice come together. And in particular, the most common substitutional impurity that you will find in any chunk of diamond, synthetic or not, is typically nitrogen. So one piece of the NV center, clearly the N piece, is the fact that you have a carbon atom being replaced by a nitrogen atom that is called a substitutional impurity. Very similar to doping in materials that you've thought about. The other, even more common defect inside a diamond lattice that occurs naturally is when there's simply a vacant lattice site. There's simply a missing carbon. Each of these by themselves is quite common. When they occur adjacent to each other, they form a particular defect known as the NV center. Okay. In particular, we could start by asking perhaps the most obvious and simple question, which is, what is the degree of freedom associated with this defect? You kind of already see, coming from a little bit of a band structure perspective, what I've drawn there from the valence and conduction band, that it's probably going to be something related to electronic states. And in particular, it turns out that this is kind of quite generic, that near this defect, there is a localized state for electrons that is actually in the middle of the band gap between the valence and conduction band, but there's a localized state for electrons where the wave function for the electronic state is now no longer some delocalized orbital in the conduction band. It is a very localized orbital that's centralized around the NV center. And in particular, although I have not yet, but I will, told you what the ground state of this electronic object is, I will tell you now that it is about 2.5. Already sort of using the language that you're very familiar with, right? So an insulator, essentially, from the perspective of electronic states. And all I'm saying is that there's a defect in the material, and near this defect, there's a localized state that electrons can occupy, and that localized state lives somewhere inside the gap of the semiconductor. And conceptually, at some level, to answer this question of what is the degree of freedom, we're going to do an analysis that's very, very similar to atomic or molecular physics. I very much like to think about this NV center as a particular defect that's like a molecule that happens to be trapped inside the solid, which is its host, the diamond lattice. And it turns out, if we put on our molecular chemistry hats for a second, the rule of the game for analyzing and answering this question, what is the degree of freedom? Very simple. The rule of the game is to count electrons and fill orbitals. Okay. So in particular, let me redraw for 1 second just the structure of the NV center for a second. Let me start by asking a question. Let's make sure everyone's awake on this Monday morning. How many orbitals, I mean, if we think about this as the defect, as the structure of the defect, how many orbitals do you expect play a role in whatever the degree of freedom in the electronic properties of the system that we're going to think about? How many orbitals are there? It's not a trick question. It's as easy as you think the answer is. Nick is already smiling. Almost. It's a good guess because it's sort of obvious that there's the carbon orbitals, right? But actually, it turns out, yeah, even though we have a substitutional purity, there's still an orbital. So actually, the answer is that at some level, you should think about 4, more or less, sp3 hybridized orbitals. Okay? There are 4 orbitals. Orbitals are associated with the atoms. So you might say, I'll denote the orbitals as sigma. They won't be that important, but notationally, just to be clear. So there's the nitrogen orbital. There's 3 indistinguishable carbon orbitals that I'll call sigma C1, sigma C2, and sigma C3. And essentially, we're going to play a game of Hund's rule, which is just asking the question, we have 4 orbitals and some number of electrons that participate in the defect, and we have to fill electrons into those orbitals in a way that respects group theory. Yeah, please, Nick.
I'm going to ask you a question.
Yeah, okay, fantastic.
You're talking about group theory. So is there an assumption that the energy level associated with the nitrogen isn't very different from the carbon?
The orbitals will have some, at the moment, with that orbital, but once you include nuclear Coulomb, as I'll do in just 1 second, you will actually find that the orbitals have different energies.
Well, I guess I would put it this way. I would imagine that you were going to get a breaking of degeneracy, but why even lump the nitrogen one in there? Like, it's close enough.
It's close enough, yeah. Yeah, it is absolutely close enough. I mean, it's like, optimal way, but yeah, that's a good question, exactly. That's right. I'll add a comment to what I say to further answer Nick's question in just a second. Other questions? Okay. So, let me ask now. So how many electrons, this is going to be a little bit of a trick question now. How many electrons do you think participate in this defect? How many electrons? 4 orbitals. How many electrons are filling these 4 orbitals?
I'll go with 3 again.
It's a very good guess. You're following the carbon route. That's right. It's right. So you would say exactly, if you were just thinking about carbon, if there are 3 lone electrons that are donated from the carbons. There's 1 electron, again, from the nitrogen as well. But nitrogen's 1 over on the periodic table. So there's an extra electron from the nitrogen. And if you remember over here, it's a negatively charged defect. That was the trick question. So you get an electron from somewhere else. Okay, so you must get donated electron from somewhere else. We can talk about where it's donated from or where people believe it's donated from, but it's somewhere else. So there's 6 electrons. Okay. And now it turns out that indeed, following Nick's point, it turns out that there's a little bit, I'll sort of leave it as an aside, it's actually very simple, a little bit of very, very simple and quite elegant group theory. In particular, the symmetry of this defect is no longer the full tetrahedral symmetry of the carbon lattice. It's actually a reduced symmetry group that's called C3V. So clearly, I can rotate by 120 degrees or 240 degrees around the NV axis. I can also reflect around any plane that involves N, V, and C. And those are the 2 symmetries that exist for C3V. And it turns out that much like you want to work in the correct eigenbasis, this is what you learn in quantum mechanics or linear algebra in general, what you really want to do is you want to write down linear combinations of the orbitals linear combinations of the 4 sigma orbitals that we've written down previously in a way that respects the irreducible representations of C3V. Not super hard to do, but something that we won't go into detail here. There's an example of one orbital, which is already pretty obvious. There's clearly one orbital, I'll call it the A1 orbital. The naming will have meaning to those that know group theory, which is literally a linear combination with coefficient alpha of the sigma orbital and an equal combination of the 3 carbon orbitals. And this orbital clearly respects the symmetry of C3V, because if I rotate by 120 degrees or any of the operations of the C3V group, the carbon atoms just get rotated to each other. So the carbon orbitals move to each other. So if they all have the same coefficient beta, then this orbital clearly respects C3V symmetry. And you write down other ones once you diagonalize the nuclear Coulomb interactions. And indeed, once you add in the nuclear Coulomb interactions, it turns out that nitrogen doesn't have that many more protons. And so you end up getting a set of orbitals, 4 orbitals in, 4 orbitals out, but these are now symmetrized with respect to C3V, as opposed to being totally degenerate without any interactions. And their names are typically A1, A1 prime, EX, and EY. These A and E's are related to the particular irreducible representation of C3V, not super important. Okay. Indeed, as Nick mentioned, EX and EY, the top 2 orbitals, are almost solely carbon, and they're degenerate. The A1 orbital clearly has some nitrogen content, and it's separated pretty far away from the otherwise degenerate EX and EY orbital by an energy that's about hundreds of terahertz, so by an optical frequency. So it's far, but not infinitely far. Yeah, please.
What happens to the E2 you left?
There is no. Reason you only A1 and E irreps. I don't think that somehow the C3V has an A2 irrep, but somehow I think for this particular defect you don't actually have an orbital at this level that falls within the A2 irrep. You mean quantitatively, like, at some level, quantitatively, why is, I'll give you an answer that I think is some very fundamental, but I don't actually. A1, as I said, the A nitrogen content. They're lower in energy. One simple way is probably, it goes in the right direction for sure, just electronegativity. So you know that nitrogen has a larger electronegativity than carbon. I suspect at the level of some simple things that means that electrons want to be in orbitals that are closer to nitrogen, and the orbitals that are just purely carbon orbitals, they have to be there because you have more carbon orbitals than nitrogen orbitals, that those are actually higher in energy. But I don't know the right answer, but at least qualitatively. Okay, so now you have to fill these orbitals with your 6 electrons, and when you fill them, you naturally fill them up, down, as you do for, 1s2, 2s2, 2p6. And now, in particular, there is 2 electrons filling an otherwise two set of orbitals that are degenerate because of this symmetry. And you can have 2 situations that happen. You know that the overall wave function of the electron psi is going to be some combination of a spin degree of freedom for the electron, as well as the orbital degree of freedom that we're talking about, that we've already written down. You also know that the wave function of the must be level, there are two possibilities that you can have. Either have the lowest energy configuration of 6 with 4 orbitals, either the spin triplet configuration and the orbital, or it can be the spin singlet configuration and it can be an orbital triplet. And almost in every case, all the types of defects that are of this form, and anything that you analyze in chemical physics, you'll find that the answer is almost always one instead of the other. 50 is pretty good odds compared to the question about the number of electrons. What do people think? Is it what would someone guess? And give me a reason. Norm is a man of infinite patience. No, not minus. I saw you raise your hand, yeah. Somebody has to venture a guess. All right, you give the guess and I'll give the reason, whether it's wrong or right. So it turns out that almost always, because it's actually the orbital degree of freedom that you want to be in the antisymmetric singlet configuration, because spin energy is typically lower relative to Coulomb by a factor of like alpha squared, the fine structure constant. Always. What the relevant states are in this manifold. So I already told you it's an orbital singlet, and you know what a singlet looks like. It's the state EX, EY minus EY, EX. There's only one orbital configuration, it is the singlet configuration. But, as I promised you, it's a spin triplet. So there are 3 spin configurations. There's in particular the up-up electron spin configuration. There's in particular the up-down plus down-up electron spin configuration. And there is the down-down configuration. So we're doing a very simple thing. At the end of the day, we're looking at this particular degree of freedom, and we've isolated the fact that, aside from filled orbitals, which don't really produce anything, there are 2 unfilled orbitals, and there are 2 electrons that participate in those 2 unfilled orbitals. So the low energy degree of freedom, the low energy physics of this particular defect has to be something related to those degrees of freedom, and there are 2 electrons. So in particular, you'll see me write this, and this is often written, that indeed, if you think about this with respect to spin angular momentum quantization, this oftentimes people write as the m sub s equals +1 state of the NV center. People write this as the m sub s equals 0 state of the of the quantum number. Exactly in the same way that when you have a spin, there are 2 plus 1 m sub s when s equals 0 and m sub s equals -1. At least you're a little immediately writing down. When we were turns out that these degrees of freedom, these states, but again, I suspect, as many of you are familiar, sorry, that was fine. if you have native Hamiltonian with external perturbations just coming from the defect in the host particle itself that looks like delta SC squared. And this is typically either called a zero field splitting, because it is a defect in the presence of zero magnetic field, or a crystalline. To be very clear here, and in particular, we are somewhat implicitly, but I think it's already pretty obvious to most of you since we talked about the symmetry of the defect, the z-axis so is you expect it, and indeed you find that the z-axis other purity in the host has a zero field splitting. In this case, it's about 2.87 gigahertz. And this, Nick is trying to calculate it, is about 140 millikelvin, if I remember correctly. So it is a microwave frequency. A microwave frequency. Good. So now let us draw a little bit. This diagram will stay with us for a little bit. Let us draw a little bit. What exactly is the structure of the degree of freedom, or the state configuration of the defect is that the electrons are in an that state can be represented as m sub s equals 0, and two degenerate states m sub s equals minus plus 1, which we'll just write in ket notation as 0 plus and minus 1. As I said already, indeed, there is a zero field splitting here that corresponds to energy delta. Sorry, I'll try to make the diagram bigger as I move forward. And this, at its very basic level, is what people mean when they talk about the spin degree of freedom of the NV center. So in many talks, if you listen to NV talks, people will talk about the spin degree of freedom of the NV center, and this is it. And you could ask the question already, can one almost, just one more second. It's a very, 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 very good question. And we will temperature energy gap delta temperature relative to the in each of the three states 0, plus, and minus 1. So, whatever you do, however you do, signal accumulation, this is precisely the reason, of course, given that we're at the MagLab, there is one very natural strategy to make this work, to get the state away from the identity, and that's to apply, for example, a very large B field such that the splitting, for example, delta effective from the Zeeman effect is greater than whatever temperature you want to operate at. And then Boltzmann thermal polarization will put all of your population into the 0 state. And from there, you can actually start to accumulate signal and do stuff. But at leading order, there's nothing we can do if we have the state simply. So it turns out, but at some level, slightly easier strategy for tabletop experiments is to search for optically polarizing. Okay. So and the amount of population lives in these 3 0 plus the ground state. And so it's a more active level approach to initializing the system. And it turns out as a strategy for defects almost always works if low enough temperature. Okay. But at some level, that doesn't buy you very much. I told you that if delta was less than 140 millikelvin, you already win. Generic strategy coming from where you can almost all low enough temperatures. But what would be great to have, ideal to have, some laser on some reason at an arbitrary high temperature that you want to work with, but still the defect ends up getting initialized. And it turns out that physics, the most interesting problems for ab initio type calculations, I won't go into too much detail about this intersystem crossing. Phenomenologically, what this intersystem crossing, I have to answer the question that was just asked a little while ago, which is what about the excited state structure? It turns out diagonalizing the orbitals, we said that there was the ground state configuration of this particular molecular defect system is 2 electrons filling the EX triplet. Immediately imagine the excited state from this is you promote one of the electrons from the now much higher. In particular, you can see that there electron is on the other side. What this means actually is that very, very high picture is drawn terribly to scale. There is a ground state and an electronic excited state. Literally think like the electronic excited state of hydrogen. We're doing exactly the same thing. There are 6 states there as opposed to 3 because I told you there were two different ways of making the orbital singlet, the EX and the EY way. And the energy difference here is about 637 nanometers, which is also about 500 terahertz. So this should be compared to the ground state splitting, which is about 3 gigahertz. So I can tell you already that indeed room temperature is much less than 637 nanometers, but much greater than delta, the zero field splitting. So it is absolutely a very good approach to imagine that the starting state of the defect, if you don't do anything whatsoever, the infinite temperature effect 3 spin states of the ground state. It turns out the magic of the inter-system crossing is that something has to go across the system. And in particular, there is, in between these two levels, another level that is the spin singlet state. Remember our poor spin singlet state over here? We said that there's another configuration which doesn't involve promoting an electron yet to a different orbital. It just involves not being as happy with respect to Pauli exclusion. And that is a spin singlet state. It turns out, I'll write this down for just 1 second, that the nature of the inter-system crossing can be explained in words extremely simply. And the statement is that if one excites, population from the ground state to the excited state, this is done via optical excitation. So you're literally moving population from the ground state to the excited state. And you can do this via absorption of a photon at sufficiently high energy, aka optical excitation. It turns out that for the NV center of the specific size of matrix elements of spin orbit, if one excites to the equivalent m sub s equals 0 state of the excited state, emits a red photon and comes back down. Gets excited up, emits a red photon and comes back down. That is called a cycling trend. And in particular, spin orbit couple. Population from the ground state to the excited state, spin population that's in m sub s equals 0 always comes back because it cycles. But population that's in m sub s equals plus or minus 1 sometimes cycles, about 70% of the time. But 30% of the time, it goes via an intersystem cross other singlet state and comes back to m sub s equals 0. And this means that you get population, you get the accumulation of population in m sub s equals 0. Just to give you some numbers, typically in an experiment, we use light at an energy that's clearly above 637. So we use green light typically. And typically within a couple microseconds of shining this green light, you get a reasonably large, 80 to 90% m sub s equals 0. Yeah, please. There is, it's just that it's just sort of a quantity. Absolutely, there's no forbidden, there's no happens if the translation element is small. Exactly, so the orbital part also has to change, exactly. So it's, you have a this you can think about essentially as something like an S dot L, where S is spin and L is orbital. And indeed, when it goes from here, you have still spin triplet, orbital singlet, and here you have spin singlet, orbital triplet. So you think about at some level, you're kind of using the S plus L minus piece of the spin orbit matrix element to move you from the excited state to the singlet. Are there any other what?
Energy cost?
Yes, there absolutely, exactly. There's an energy, there is the energy difference here. I don't remember exactly what the energy difference, but certainly there is some energy difference associated with that, yes. Right. But you're relaxing, I mean, at some level, I mean, you've already given, I mean, maybe one way to think about this is like, sort of the question is sort of, how did I get there in the first place? And actually, in some sense, you get there by absorbing a photon that's green, that's much higher energy than 637. Then actually, you make a bunch of phonon excitations, and then you're relaxing from the excited state to the singlet state. So you're making phonon excitations. You excite something called the phonon side. But the energy initially to get from the ground state all the way up over there is via the absorption of this green photon. Other questions? Excellent questions. Yes?
Why not just use 637 and not have phonon?
Exactly. So that's super. You can use 637, but only typically at low temperatures. It turns out that the broadening, it's a super good question, the thermal broadening from the excited state is pretty large actually, and it's typically much larger than the frequency spread of a laser. So if you cannot address any of these transitions directly, because you think about all of these transitions as just one broad amalgamation of lines coming from thermal broadening. So at low temperatures, a much more efficient strategy, as Professor Vofik is alluding to, is this strategy. At low temperatures, you don't go resonantly at all, you just do it resonantly, and you just use selection rules literally because you can actually resolve the energy levels and directly do photon to photon, directly between these different levels. Super. Yes, please.
Pretty low, so you don't really worry about.
Yeah. Very, exactly. Basically negligible. Exactly. That's right. Yes.
Statistically, it would be very unlikely to absorb 2 photons at a time, but
Not so unlikely, actually. Exactly. It's actually not so unlikely, and actually absorbing 2 photons actually causes ionization. So actually absorbing two, there it is. Absorbing 2 photons happens actually. There is some finite cross-section for that to happen. You have to be careful with the amount of optical power that you use and the amount of duration that you shine the light for. But actually, what happens is that you can actually absorb 2 photons and kick yourself into the conduction band and essentially ionize the defect. So there's always some balance between that rate of ionization and the rate of polarization. Good question. Yes, please.
do you have to continuously apply the optical light? Because otherwise, thermally, all the states of the quantum mix again?
Yeah, very good. The time scale on which that happens, that's super good questions, actually. So, as I said, the time scale on which optical polarization happens is about a microsecond. The time scale on which things relax to equilibrium, to thermal equilibrium, which is again this 1/3, 1/3, 1/3, is on the order of 10 milliseconds or so. So you have some reasonable window of time between a microsecond and 10 milliseconds to do your experiment. But indeed, after 10 milliseconds, you're back to that state. It turns out that, I'm not going to go into this, but the dominant reason why the system gets back to being this sort of 1/3, 1/3, 1/3 is from spin-phonon interactions. So even if you decrease your temperature a little bit, you can push that 10 milliseconds to many seconds or many minutes. Another good question. Other questions? This is really wonderful. Okay, fantastic. So now that we have an optical strategy, it's basically the acknowledge the fact that also something along the way that we haven't talked about. In particular, along the way of these discussions, we actually also gained a readout mechanism. And the readout mechanism exactly goes back to this statement over here, to this dichotomy. In particular, you can clearly tell that if you use your figure of merit, your measurement, as the number of photons at 637 nanometers that I collect, then if my NV center starts in the m sub s equals 0 state, I will scatter more 637 nanometer, these are red photons. And if it starts in the plus and minus 1 state, it will fluoresce less. Because 30% of the time, it's going through a totally different pathway with totally different energies. It'll still emit a photon, 1042. But if you filter 7, you will not see the 10. And this means that you, in fact, have gained something from this intersystem crossing, and that is the fact that your system also exhibits something known as spin-dependent fluorescence. Approximately the most obvious naming. It is a fluorescence count that depends on the spin state. Okay. So now, let me tell you, running out of time. Okay, we'll figure it out. Let's now talk about the simplest sensing experiment that one could imagine doing. Okay? Well, in particular, I've already convinced you so let's, and also as Professor Chubukov mentioned, indeed, with respect to superconductivity, one of the central signatures in addition to transport is the Meissner effect, and that's the repulsion of magnetic fields. So let's talk about how exactly an NV center would sense a magnetic field. And to do that, before we turn on the magnetic field, let's imagine what the signal would look like, and we'll show data in the next lecture. What the signal would look like first in zero magnetic field. First at zero magnetic field. Well, at zero magnetic field, before you do anything, you have one-third population in the 3 spin states. Then you polarize by shining a little bit of 5/3 nanometer light. And now the population, let's say, is predominantly in the m sub s equals 0 state. And then you do old school magnetic resonance spectroscopy. Very well-known thing at the magnetic field lab. And this magnetic resonance is a little bit different than usual NMR or ESR experiments where you use a pickup coil to be able to look at the signal. Instead, because of the spin-dependent fluorescence, you just look at the number of counts. You just look at the number of counts, for example, on a photodetector or an SPCM, whatever your favorite thing is. And by microwave spectroscopy, I mean that you change the frequency of the microwave, but you keep the power of the microwave fixed. Clearly, something's going to happen on resonance. When you're away from resonance, the microwave is not going to be able to excite population from the 0 state to the plus or minus 1 state because you're off resonant. When you hit resonance, you will move population from here to here, and that will cause a dip in the fluorescence, precisely because the plus and minus 1 state are less bright. And when you again go above resonance, it'll come back because you're no longer resonant again. You're just resonant, you're just blue detuned instead of red detuned. Okay, so that is what an ODMR, optically detected magnetic resonance spectra of the NV center looks like at 0 magnetic field. But we're talking about sensing external magnetic fields. So let's say that you have a material of interest, and it is affecting your magnetic field or changing the magnetic field, says that B does not equal to 0. Then again, initially, you will have the fact that the plus and minus 1 states have a Zeeman splitting coming from the magnetic field itself. Let's call this delta Zeeman. In addition to the 0 field splitting that you have between the states delta. At time t equals 0, if you don't do anything, again, the population is equal 1/3, 1/3, 1/3, nothing to do. But if you shine light, now again, all the population goes into the 0 state. And now let's draw the exact same plot. Let's draw the exact the microwave field becomes resonant with the -1 transition, the 0 to -1. And the second feature happens when it becomes resonant. And the splitting between these is precisely given by 2, the G factor, the more Bohr magneton magnitude field projected along the NV axis. And that, you know what the Bohr magneton is, you know what the G factor is about electron G factor. So from this, you can precisely measure the splitting of this. But it's kind of nice to do. So you can ask ourselves a very simple question here, which is, what limits the sensitivity? So I'm going to tell you that for single NV centers, typically the sensitivity that you can get, the best sensitivities are on the order of 1 picotesla per square root hertz. It means that if I integrate my experimental signal for 1 second, I can measure a field difference of a picotesla. Extremely, extremely good. I think as far as I know the record. But now this is very important, and this is a very simple approach. It's not the only thing. It's one. What limits the sensitivity? Why is it not infinitely sensitive? Already kind of gander it a little bit from the pictures that I've drawn.
NV axis also has to be aligned correctly.
Sure, but whatever your NV axis will be something, and you're always just measuring the projection. So even if you have an external field, you're measuring the projection of that. It'd be good, yeah, exactly. So your diamond will have some orientation, and you will know that. Beautiful, beautiful. This is coming, and this natural line width typically is also the inverse coherence time. This is partly precisely the reason when people talk about qubit, because the coherence time is the last statement, I promise. So it turns out the sensitivity of any such defect-based sensor can always be written in a universal formula. That's the line width B, number, and T is the integration time of your experiment. Okay? And just, I'm going to sound like Andre, just one more thing. So in the limit where you have extremely dilute, like I was promised you, single NV centers, it turns out this line width is limited by magnetic fluctuations coming from nuclear spins of carbon-13 isotopes. In the dense limit where you have many NV, still not as dense as 10%, like we're thinking about for doping, but more dense than a single defect. Paramagnetic things in the system right about here. I didn't quite get through everything I wanted to, so I'll pick up here at the beginning of lecture 2. All right, thanks a lot.
Questions?
Yeah.
I just had a basic question that the NV axis that you mentioned, it need not be that Z axis that we talked about earlier, right?
Z is always defined to be the NV axis because that is the quantization axis, but it need not be aligned with any external magnetic field.
No, but in absence of the spin orbit coupling, this the plus one direction of the triplet could be anything, right?
Sorry, so I mean, there's always, I mean, in some sense, I don't know if you're asking a discrete question or a continuous question. Are you wondering whether or not, I could quantize angular momentum in any direction, or are you wondering whether or not I can distinguish NV versus VN? Is it I think it's the first one, I guess.
I'm asking that as far as the triplet, the direction of the triplet is concerned, why is that axis special?
Because of the symmetry. I mean, C3V symmetry, there's only rotational symmetries around.
It does not affect the spin rotation. That's my question, right?
It does not affect the spin rotation. Let me think about that for 1 second. So you have, I think it does. So I think it's still, I think probably you're right at the level of what you said, but I think what happens is if it were a single spin, you're absolutely right. But because it's 2 spins, I believe what's actually happening is that you get the orbital piece because of dipole-dipole interactions. So here's what actually happens. If you have 1 spin, you're absolutely right, nothing can change that. But you have 2 spins, and they have dipole-dipole interactions that care about R, and they live in the orbital. And in fact, the thing that's delta in front of delta SE squared, microscopically, it comes from magnetic dipole-dipole interactions between these 2 spins is actually what gives you delta. So I think that R is where you actually get that, where you know about the rotational symmetry in real space.